Okay, so now in this video I'm going to show you the first method, and the first method is kind of a simplistic model, but I do like the second method, so I'll show you both the methods so you can choose your own. So let's start with it. Okay, first method one. Okay, so let's start with it. So in this method I do want to write the last equation so that I will have a reference. Theta is equal to L upon under root 2 mu. Here we had 1 over r square, and we had the energy minus L square upon 2 mu r square plus g m1 m2 upon r. And here we had d of r. Right, so our first method revolves around this. It's called as the substitution method. Alright, so what we do is we substitute this 1 over r, we substitute u for 1 over r. Now I really want to emphasize one thing: do not confuse this this mu and u. I know it looks similar because of my writings, but do not consider it as same. Mu represents mass and u represents 1 over r. I know, but I cannot help. These are the standard notations. I have to stick with it, and also that's kind of an easier simplistic model than to use other complicated notations. Now I differentiate it in order to get du, which is minus 1 over r square. Get minus sign because it's in the denominator, and that is dr. What we do is we substitute this substitution onto this equation, so we get d theta is equal to minus L upon under root 2 mu d of u. Alright, we have E minus L upon 2 mu. Okay. I keep this as an r square for now. Okay, yeah, I'm sorry. This is okay. I'll rewrite this. Minus L upon under root 2 mu d of u. This is u, alright. This is E and L upon 2 mu u square plus g m1 m2 u. Okay, that's it. Yeah, that's it. So what we do now is make the absolute value of the coefficient of mu square to be unity. So what I do is so what we can do is we can multiply the numerator and the denominator by the factor. Okay, let me write it down. Multiplying numerator and denominator by 2 mu L, it's mu, by this factor. So we will have the following. So we will have following d theta equation, which is d theta. Okay. Can't help. It's disgusting. I know it looks disgusting, but give me a second to explain it. u square plus 2, yeah, we do have 2 mu m1 m2 g upon l square u. Here is dv. Now I know it looks disgusting, but give me a minute to explain it. So this is what you get if you multiply by this factor, and you will get this equation. Okay, I know it looks dirty, but we can analyze it by the following procedure. If you see the left hand side of this equation, the left is, this is the left, so left hand side is this equation LHS. This is LHS and this is RHS equation. So LHS is dimensionless. It's dimensionless. So what I can do is I can analyze the equations on the right hand side. The right hand side equation is, okay, I'll take this for this matter, mu g m1 m2 upon l square. Okay, it must have, okay, please note the wordings. It must have dimensions of u. But what is u? U is 1 over r. It means it must have a dimension of length inverse, right? So see, it's actually viable to see this. See this, here the dimension has been taken care of. Here we have to take here, so we need a dimension so that to make all this dimensionless, so that we need a dimension of u square over total of here. Alright, it has a dimension of u square over here, it has a dimension of u square over here, so it has a dimension of u, so it must have a dimension of u over here, so that this has a square root, so u square under the root will become u, and we do have a dimension of u, so the u and u get cancelled, so we have a dimensionless term, which is consistent with our LHS side. See, it's that simple. It's not easy, it's not difficult at all, it's easy. So this must have a dimension of length inverse. So we define a quantity called r naught, which is given by l square upon mu g m1 m2. Now this is semi-lattice rectum. Please note this. This is very important. The r naught L square upon r naught L square. R naught is equal to L square upon mu g m1 m2 is semi-lattice rectum. Okay, so we define our d theta in terms of minus. I'll ponder, I'll answer your questions about what the semi-lattice rectum is more as we proceed our discussion on central force motion. So you need to have little patience. This is 2 mu e upon L square, and we did have u square followed by 2 u, right, 2u, and we define this quantity. Must have a definition of L, then length inverse. So we define this quantity called r naught, right, so that it is consistent. We define a quantity called r naught, and this is said to be a semi-lattice rectum, and I asked you to have some patience so that I can define it over the course. So we get r naught because it has a dimension of length inverse, and now it has a definition of length inverse, so it's practically done and done deal, right? That's cool, right? That's cool. So what I can do now, I want to rewrite the denominator to express in terms of what is called as eccentricity. So uh, I urge you to go through the basics of conic sections. It's not difficult, okay? It's not at all difficult, but it's important. So d theta, okay, this is 2 mu e upon L square plus 1 upon r naught square minus u square plus 2u r naught, right, r naught upon 1 upon r naught square. What I did here is I added a quantity and I subtracted by the same quantity, so that our initial equation is intact. All right, this is some kind of a manipulation. All right, you need to learn this manipulation, because whenever you see an equation, you need to know what that equation demands. You need to understand what the equation is asking. What's the demand from that equation? You need to answer that question. In order to answer that question, you need to visualize the equation. You need it should happen that to be a great physicist, it's been said, to be a great physicist, the equation should be your best friend and it must talk to you. It's incredible power if you possess that. You are going to be an incredible physicist if you possess that kind of quality. So yeah, so it's half because I want to forget this factor. So I added the quantity and I subtracted by the same quantity. So you'll understand why I did it, because it's some kind of a manipulation. And what I can do is, I can see this being a formula of a square am I seeing it right? Yes, a square plus 2ab plus b square minus b square. Right, I can use this formula. Okay, I can see this, right? So what I'll do is, the first term doesn't change at all, and there's an r naught square over here, and here's a minus. I'll take that minus outside, so that, okay, now it's u minus 1 upon r naught the whole square. Alright, no difficulty at all, right? If you see it's difficult, you can go back, go back few minutes behind and see how I did it. I did nothing. I just added this 1 upon r naught square. I subtracted by the same quantity, so that our initial equation doesn't get changed. Then I used a square plus 2ab, sorry, a square minus 2ab. Okay, let me write it down. Then I used the formula of a plus b, sorry, a minus b the whole square formula, which is a square minus 2ab plus b square, right? I just used this equation, use this formula over here, because I was able to see that it was forming this kind of equation. So I got an equation which is super nice as compared to the ugly one we saw before. Alright, so I'm still not satisfied, because I don't want too many terms in the denominator. It's hectic for me to keep a track of each and every term if it's in denominator. So what I'll do is, I'll try to bring this term above. So we'll get, see, it's not hardcore mathematics. I'm just manipulating each in terms, and the manipulation is simple mathematics, and it's not kind of hard as you might see it. So it gets multiplied by r square l square plus 1. Yeah, I know r naught should come, but the problem is I can keep it whatever I want. For now, I'll just keep it r square, and if I find it's not working, I'll change it. And get r naught u minus 1 the whole square, and here is Alright, that's beautiful. Done. Great. So I define a quantity over here. Now it's time to define this quantity. This quantity 2 mu e r square upon L square is denoted by the following symbol. So this is a constant. Yes, why can I define this as epsilon? Because it's a constant. You see, this term is constant. See, constant. So it doesn't matter. Alright, so I can define it as some kind of an equation, and mu square is what I define. So I get epsilon is 2 mu e okay, just a second. I don't see this going anywhere, so okay, what I'll do is I'll define okay, so I have one here, so okay, fine, I'll rewrite this equation onto the next page, and we can proceed further. Hope you can see it. Okay, let me write that equation again. Okay, what's wrong with the focus now? d theta is equal to minus r naught du upon 2 mu e r square L square plus 1 r naught u minus 1 square, and there was a raised to the power half square root term. So I define the quantity called epsilon, which is given by, so yeah, rather than writing it, I'll just define it here. 2 mu e r square upon L square. So this particular term is what I define to the power half, because yeah. Okay, so this is what I call as eccentricity. And you need to revise your conic sections to get a strong grip over this following topic. Alright, so I do recommend it, but if you're short on time, say if you're very nearing to your examination, so what you can do is just accept it, because the geometrical reasoning gives you a strong foundation to understand the topics better and better, and the topics like center force motion needs a very strong hold of conic section. The geometrical reasoning is very important, so just take a look. D theta is, I can rewrite this in terms of epsilon. Epsilon square minus r naught u minus 1 to the half. Okay, we got an equation. So now it all lies within u. So if I take r naught, okay, this looks like gamma, so r naught u minus 1 is equal to epsilon cos alpha. So r naught du is equal to minus epsilon sine alpha d alpha. I just differentiated this term, so get rid of 1. Alright, so why this is equal to this, it needs a strong geometrical reasoning again, but if you don't if you're not interested in this, you can simply accept it as lemma or something, but I don't encourage you to do it. You're a physicist, all right, we are not a mathematician. So what mathematician does it, if he wants to prove a theorem, he needs to prove many things. Rather than proving many things, his whole aim is to prove just a theorem, he will state lemma and he will just keep moving forward to prove theorem. Like, I'm not interested in this, I'm interested in proving theorem. So that kind of attitude do gets developed, but as a physicist I don't encourage you, but do get a strong geometrical reasoning behind this. See, I know we all are short of time with our examination rolling around, but if you want you can accept it as lemma, but that's all I can do for right now. Okay, so we got r naught du is equal to, okay, I'm sorry the focus being so weird today, sine alpha d alpha. This is what we got after differentiating that term. So what I do is I can state d theta is minus epsilon sine alpha d alpha upon epsilon square minus epsilon cos square alpha half to the power half, which is d alpha. Yeah, so if I integrate this term, d theta is equal to d alpha. So this is my d alpha, right? Let's see. What I did is I stated what's called as an eccentricity, then I substituted that eccentricity to get d theta, then I stated r naught u minus 1 is equal to epsilon cos alpha, then we differentiated this term to get rid of this minus 1 and we got this term, which is simple differentiation. Then we can write d alpha is equal to r naught du upon minus epsilon sine alpha. So what we did is we wrote r naught du is equal to minus epsilon sine alpha is what we got. Then I can state this equation d theta equation in the form of alpha, with alpha and eccentricity, which is our newfound equations. Then this is nothing but d alpha, then I integrate these two equation and I find, alright, this is an integral equation, but do note it is, you will get a constant, right? Because they are indefinite integrals. Do keep that in mind, alright? Do keep that in mind. It's d alpha. Do keep that in mind. It is an indefinite integral. It doesn't have limits. You will get a constant, and that particular constant will decide your outcome. So now the constant. Now about the constant, I have to say a few words about the constant. The constant is in my hand. I can select what constant I want as long as it satisfies the ranges of that particular parent equation. So what I do is I'll select, I hope you can see this. Okay. Select the constant. Select the constant such that my theta is equal to alpha minus pi. So what I can get, cos alpha is equal to minus cos theta. What I did was I selected a constant such that my theta is equal to minus pi, and I got a cos alpha equation which is equal to minus of that cos theta. Alright, these are same in magnitude but just opposite in sign. You can see that cos alpha is equal to minus cos theta. So what I can do is I can find r is equal to, I'm just restating my earlier equation. So in terms of r, so I'll get r naught is equal to 1 minus alpha cos theta. Right? But, okay, just keep this equation. But if I choose the equation, this constant, as I told you, the constant the constant is in my hand. I can choose whatever constant I want to. So if I choose the constant, so if we choose, really sorry for my handwriting. We choose constant to be 0, I get the same equation, but I'll get a plus sign over here. So this is some trajectory reflected about the vertical axis. This equation geometrically represents a trajectory reflected about the vertical axis, and this equation represents a trajectory about the horizontal axis. So we can combinedly write this equation as R naught 1 plus minus epsilon cos